Today we will start talking about a new topic, which is the dynamic analysis in time domain. So first we will start talking about the basics, a simple single degree of freedom system, and we will try to solve the governing differential equations by using the analytical methods, and then we'll switch to the numerical methods. Now let's say that I have this single degree of freedom system. I have a mass that can move. So I have a spring attached, which represents the stiffness, and I have a dashboard attached, which represents the damping in the system, and I am applying a dynamic force to the system. Now if we write the equilibrium condition for this dynamic system, on one side I have the applied forces. Here I have PT, the applied force, and I have the resisting elastic force, Fs, that will be equal to K times U, and I have a damping force, and I'm defining the damping as it's depends on the velocity, and this system should be equal to mass times the acceleration on this of this member. And by looking at this equilibrium equation, we can write the equation of motion. So we say from the above free body diagram, we obtain the equation of motion for a general single degree of freedom system. And that would be equal to P of T equals to, P of T minus elastic force K times U minus damping force C times U dot, and that should be equal to M times U double dot, and rearranging this equation will give me the equation of motion for a general single degree of freedom system. So how do we solve this differential equation? So we will be examining 4 cases. The first case, we don't have any PT, no excitation force, but some initial condition. We call it a free vibration, and we will examine the free vibration again in 2 cases. In the first case, we don't have any damping, and in the second case, we have damping in the system. Now let's start. So the first case will be undamped, free vibration, no damping, no dynamic force, just the initial conditions. So in that case, my equation of motion will have the following form: M times U double dot plus K times U equal to 0. Okay, so in order to solve this differential equation, I'm assuming that let U is equal to e to the power S times T. Then put it into this main equation, I'll call it equation star. Then I have the following equation, e to the power st in parentheses m times s squared plus k equal to 0. And this part is my characteristic equation. E to the power st cannot be equal to 0, so this should be equal to 0. This is characteristic equation. So I'm obtaining the following: ms square plus k must be equal to 0, and from that the roots of this equation s1 and 2 will be, it will have a complex root plus of minus I in square root k over m, and this is called the natural frequency of the system. And I can just directly write that the roots of that characteristic equation is equal to plus minus I times omega n. In that case, my u will be equal to a constant a1 e to the power s1 t plus another constant a2 e to the power s2 t. And if I put the roots into that equation, I have the following equation: a1 e to the power I wn omega n t plus a2 e to the power minus I omega n t. Now, if we recall what the cosine of x in the complex space is equal to, so that's cosine x equal to e to the power ix plus e to the power minus ix divided by 2. And if we again write the sine of x in complex space, that would give us e to the power ix minus e to the power minus ix divided by 2i. So inserting these two relationships into this equation gives me the following: so I call this one equation plus. So equation plus can be written as u of t is equal to a times cosine omega n t, a constant, times cosine plus another constant times sine omega n t, and these constants, or the coefficients a and b, depend on the initial conditions. So we are saying that at t is equal to 0, u is equal to u0, du over dt, which will give us the velocity, is equal to v0. Okay, by using these initial conditions, I can rewrite the displacement equation. U of t will be equal to u0 cosine omega n t plus v0 divided by omega n sine omega n t. So that's the solution of the governing differential equation for an undamped free vibration. So that's our simplest case. Now let's take a look at the case when we have a damping. So damped free vibration. So my equation of motion will have the following form: m times u double dot plus c times u dot plus k times u is equal to 0. So let's call this one equation star. Again, my starting point is the same. I'm saying that let u is equal to e to the power st, and that will be my equation 1. So inserting 1 into equation star gives me the following: e to the power st in parentheses m times s squared plus c times s plus k is equal to 0. That's the characteristic equation again. Now, let's take a look at the roots of this characteristic equation. So S1 and 2 will be equal to C plus and minus C squared minus 4 times MK divided by 2M. So depending on what we have inside the square root, we have different behavior. So if C squared, let me write it at the bottom. So if C squared minus 4 times MK smaller than 0, then we have a complex root, and we call this solution or this result as a underdamped case. So since we have a complex solution to this equation, the complex, we can convert it into cosine and sine, and at the end of the day we will see some oscillations in our results. The other condition could be, or the possibility is, having this value equal to 0. So this is called the critically damped system. And the final case is C squared minus 4MK could be larger than 0, and that will be the overdamped system. In that case, if you have an overdamped system, we don't see any oscillation in the system, just a decay curve. So here we are interested in the underdamped case. So we will be solving the underdamped case. In order to solve it, we will make some definition. So we say that let Cc is equal to square root of 4mk. So that's the value that makes this part of the equation equal to 0. So that's the critical damping ratio. Not ratio, but it's critical damping. Now we define damping ratio as follows: C over Cc, and the vibration frequency omega d is equal to 1 minus xi squared multiplied by the natural frequency of the system. So with these definition, the solution of equation star is, of course, we are writing it for an underdamped system. U of t is equal to e to the power minus psi omega n t. Of course, I'm putting the boundary condition in its place. U0, sorry, the initial conditions. U0 cosine omega d times t plus V0 plus psi omega n U0 divided by omega d sine omega d times t. So that's the solution for a damped free vibration. Now let's see how we can solve the equation of motion when we have a harmonic loading. We will first examine it for an undamped system. So we will be looking at undamped vibration under harmonic loading. So we can analytically solve the harmonic loading case only. I mean, not only, but in an easier way. So as the loading part gets complicated, the solution will be complicated. So m times u double dot plus k times u will be equal to, I'm defining the harmonic load as follows: P0 multiplied by sine omega is the frequency of the loading multiplied by t. Again, let's call this one as our equation star. Now in this type of differential equation, we will examine the solution in two parts. One of them we have the UC, the complementary solution. It's the case when this no loading, m times u double dot plus k times u equal to 0. That's our complementary solution. And plus the particular solution. So we already obtained the solution for the complementary part. Remember that we were solving m times u double dot plus k times u equal to 0, and from that we obtain the complementary solution as a times cosine omega n t plus b times sine omega n t. Now the particular solution, let's take a look at it. So I'm saying that let up is equal to c times sine omega t. So when I just assume that u will have this form, u double dot p will be equal to minus omega squared times c times sine omega t. Again, let's call this one equation 1. So inserting 1 into star, we get C as equal to P0 over K. This is the static deformation multiplied by 1 divided by 1 minus w omega over omega n squared. So what we observe here is when omega equal to omega n, this denominator becomes equal to 0 and the displacement goes to infinity. We call this case as the resonance case. Now our ut will be then become equal to the complementary solution a times cosine omega n t plus b times sine omega n t plus p0 over k 1 over 1 minus omega divided by omega n squared multiplied by sine omega t. So with the initial conditions, A will be equal to the initial displacement and B will be equal to velocity divided by omega n minus p0 over k omega n divided by 1 minus omega over omega n squared, and that will be the solution for undamped vibration under harmonic loading. And our final case will be damped vibration under harmonic loading In that case, our equation of motion is as follows: m times u double dot plus c times u dot plus k times u is equal to p0 times sine omega t. And again, let's call this one equation star. I will just directly give the solution. So the solution of the above equation u of t is equal to e to the power minus psi omega n t a times cosine omega d times t plus b times sine omega d times t plus c times sine omega t plus d times cosine omega t. And in that case, the c will be equal to p0 over k 1 minus omega over omega n squared divided by 1 minus omega over omega n squared plus 2 times psi omega over omega n squared. That's the coefficient of c, and d will be equal to p0 over k. At the numerator we have minus 2 times psi omega over omega n divided by 1 minus omega over omega n square plus 2 times psi omega over omega n squared. So that's the solution. So in order to find A and B, again, you will take a look at the initial conditions and make sure that they are equal to U0 and V0. So these are the analytical solutions of the 4 cases: free vibration, no damping, free vibration with damping, and we examined the cases where we have only the harmonic loads. And when you take a look at the result, so this will give me the U at every time instant. So we are solving the whole, obtaining the solution for the whole time domain at a single equation. So we were able to get this solution because our loading is simple, is a simple harmonic loading. So as I said before, as this load becomes more and more complicated, the solution sometimes we can obtain and sometimes maybe it's not solvable. So that's why when we have a dynamic case, we prefer to use numerical methods. So what we are going to do is we will take that simple case and take a look at the solution of these equations. Now let's take a look at the solution of a single degree of freedom system. Again, we are solving this simple case where we have a moving mass and we apply an harmonic load to it, an elastic spring. So here we are saying that the stiffness is equal to 100. We have a damper, and for the damped vibration cases we use the damping ratio as 10%. The mass is 400 and we give a initial displacement U0 that's equal to 1 and no initial velocity. So what I did here is I just write down the equations that we derive for the undamped free vibration. This is the solution, and we have undamped vibration under harmonic loading. That's the solution for that case. Now we have the damped vibration, it's damped free vibration, no loading. That's the solution. And we have the damped vibration under harmonic loading. So this is the C and D coefficients. We say that when displacement is equal to, time is equal to 0, we should have U0. So that's why that will be our coefficient of A, and that will give us the coefficient for B. Now let's take a look at the solution now. I first examine the free vibration case. Now, as expected, the red one is the undamped vibration, so it starts to oscillate with the same amplitude. It goes from +1 to -1, and there is no decay. It always reaches to the same peak points. So here I said time, but you should multiply this with delta t. This is actually represents the time steps that I'm using. Now the red one is the undamped vibration, so you can determine the period of the structure by just looking at this time difference between the peaks. That will give you the period of the structure. Now the damped structure, as you see, we start with 1. In the first cycle it's smaller and it gets smaller at every cycle. We see the effect of damping, and when you plot the top points of these curves, you will get your decay curve. Okay, and this is called a decay curve. And depending on the magnitude of your damping, you will get a steeper decay curve or more flat decay curve. So that's the result in the time domain. Of course, since we have a single degree of freedom system and very simple loading, by looking at this time history results, we can actually see something. We can make comments about the results. But when we have a multi-degree of freedom systems or more complicated loadings, it's very difficult to say something by just looking at the results in the time domain. So it's very common to convert this time history signal and look at it in the frequency domain. So for this purpose, we usually use the fast Fourier transform. So I did it. I convert this time signals into frequency domain by using the fast Fourier transform of this MATCAT software that I'm using. And the result is as follows. So what I see for the undamped vibration is the peak, and this peak happens at frequency equal to 0.5. And if you calculate the natural frequency of the system, you see that it's also equal to 0.5. So here we are observing a peak at the natural frequency of the system. Now the difference between the damped and the undamped vibration is as follows. See, in the undamped case, the amplitude at the natural frequency at 0.5 is much higher than the amplitude of the damped vibration. This makes sense because, as you see, there's no decay in the undamped vibration. So that's why it has a larger amplitude here. We see a decay in the damped vibration, so the amplitude is smaller. The other difference between the damped and the undamped vibration is the width of that peak. I mean, maybe it's not very clear because the FFT software doesn't give me much resolution here, but it's very common to see for the undamped vibration, you see a very sharp peak, something like that. But when you have the damping in the system, the peak becomes more wider and it covers a larger frequency interval. So for an undamped, when we have damping in the system, we expect to see a curve like this. If you don't have a damping in the system, it's a very sharp peak. Okay, so that's what we see in the frequency domain for a single degree of freedom system. So this is the case with free vibration. Since it's a single degree of freedom system, we see only oscillations with respect to the natural frequency of the system, and that's it. There's no other oscillation in the system. Now, if we take a look at the second case, so I define P0 as equal to 2000 and the frequency of the applied loading is 5. So it's a faster loading, it's faster than the natural frequency of the system. So when we look at the time domain, so in addition to the natural vibration, okay, remember that we start from the 1, so the system starts to oscillate in its natural period, but at the same time we see the effect of the applied loading, a very fast loading, but we see its effect. Again, undamped vibration will have the same amplitude, it doesn't change, and we see a similar decay curve. Maybe it's more difficult to track because the effect of the loading also confuses us. It makes very difficult to see the peaks, but again we see a decay here. Again, when we look at the results in the frequency domain, this is what we see. So this part is related to the natural frequency of the system, but we see another peak right here, and this peak is equal to a frequency that's equal to 5. So actually this is the effect of the applied loading, a harmonic load having a frequency of 5, and this is the effect of the natural frequency of the system. So the effect of loading doesn't have any differences in the peaks or in the width, but again here we have a very sharp peak, a larger amplitude for the undamped vibration, a wider peak, smaller amplitude for the damped vibration.